means the sign. Okay, so if it's entered, it's positive. If it's going out, it's negative. Okay. So here is a simple proof for this equation. So here, for the left side, we can see this is the sign, right? So we can simply add all of them. Let's look at this figure. You can see the I1 is entered into the node, so it is positive, right? And I2 going out minus, I3 going inside positive, I4 going inside positive as well, and I5 go out minus, right? And now we're going to integrate both sides of this equation, and for the left side we will have this one, and we get this one, this one, this one, this one, this one. Okay. Sorry. Okay. And we can see this integration is actually the QT from the definition. Remember? And then we can have this part equal to Q1 to Q5. And from the conversation of charge law, we know the net charge QT should be 0. So we can say our IT equal to 0 equal to sum IN from n equal to 1 to n. Okay, please notice here I use the blue for the I1, I3, I4, and we can notice they are all going inside into the node, right?
Yes.
And I also use red for I2 and I5. They are going out of the node. What does this equation mean?
The coming current is equal outgoing current.
Yeah, this means the current going inside is equal to the current go outside of the node. This one is the extended KCL law. That means just now we talked about a node, right? And now we're talk about a boundary. That means we use a boundary and make it large, and then we get this closed boundary, right? And if we close it, it will become a node. Okay. And for this closed boundary, it also can be considered as a big node. Okay. So for this big node, the current go inside is equal to the current go outside. Just consider this part as a big node. Understand? Okay. The extension to the equivalent circuit of current source in parallel. Here we can see this one is a simple figure, and we can see we have I1, I2, I3. We have 3 current sources in parallel, and this one can be considered as a single current source. This one and this one are equivalent. And what is the value of IT?
Okay.
What is the value of IT?
I1 and IT is equivalent.
Yes, IT is equivalent of those 3. But what is IT?
Oh. I1 plus I3 equal I2.
Okay. If we say these 2 circuits are equivalent, they must have the same UI relationship. Okay. The associated reference direction is as this one, and we can suppose we connect resistance here, resistance R here, can we? Okay, so the VAB for node A and node B is like this, as the sign. The positive side is A, the negative side is B, okay? And we can see the IT, the current, is go inside into the node A. Here is the same. So, for this figure, we can notice for this part and this part, we can see it has the same UI relation on the port. Understand? For these two ports, they have the same UI relationship. They have the same U and they have the same I as well. Understand? Okay. We can focus on this resistance. We can see from the VCR, you know what VCR for? What VCR for?
Voltage current resistance. V equal IS.
Voltage current relation. Okay. So the VAB for a resistance, we know it's Ohm's law, right? Our V equal to I R. Okay. So our VCR is VAB equal to IT times R. And for the value, we can see for KCL law of this node, our current going inside is equal to the current go outside, and the sum of this node is equal to 0, right? So our IT should be I1 minus I2 plus I3. Okay. Therefore, if we make IT equal to I1 minus I2 minus plus I3, we can say this one is the equivalent circuit of this one. So why do we make this?
To find this node voltage or next current, we have to do this.
Yes, but the main purpose of this is for the circuit analysis. We're trying to simplify the circuit. Understand? Yes. So for the original one, we can find we have 3 current sources inside. But if we make this equivalent circuit here, and we can find our sources is just 1. And this circuit is simplified. Okay. Now we're going to see the equivalent circuit of sources in series. Let's look at the figure. We have 2 nodes here and a current here. Here we have 3 current sources in series, and they all have the same value. Okay. 3I in series. So we say the equivalent circuit will be 1 current source with I. The reason is the branches with the current source is decided by the value of the source itself. Okay. And those 3 should be the same value, I. Okay. And the next one is this. If we connect any element with the current source, and here we can see if we connect a resistance on this port, it's equivalent to this one. Why?
Because this current is series version, and any element.
Why? It is because for this port, okay, the current is decided by this one. It's not affected by the value of this element. Okay, so we can notice here for this figure it also has the I. Okay, and when the R is the same for VCR, we know V equal to IR. So this one and this one is the same. So in our practice, if we have any element in series with the current source, we just delete it. Understand?
Okay.
Because it is no use in the circuit. So here, please notice here, I say except the case to find the voltage on the inner element. What does this mean? That means if we want to if we want to try to find out the voltage on this element, we cannot do it. Understand?
Okay.
Because it has current inside, right?
Yeah.
It has current, so it has voltage, but it doesn't affect the outer current and doesn't affect the outer circuit. This part is the inner circuit, and this part is the outer circuit. So the property is for a port. Okay, please remember, the property is for a port, for this port. So here is the explanation. A current source besides the port current I, okay, but the port voltage V is decided by the outer circuit resistance R here. It is not affected by any inner branches. When you remove this element, the voltage and current in R still the same. Okay, additional contents. For a circuit with n nodes, we can write n minus 1 independent KCL equations. That is the thing we need to remember. Let's look at this figure. How many nodes do we have?
1, 2, 3, 5. Oh, node loss, sorry. 1, 2.
Okay, for this one, we can say we have no node with three branches. So for one definition of node, we can say it is no independent node here. Okay, so for this figure, we use KCL law or KVL law.
Okay. 2 nodes.
So for this one, we can say it is no KCL equation because we didn't have any independent node inside. Because, for example, we take one from here. Okay, take one from here. We can say the current going inside is equal to current go outside.
Yeah.
So
it's not no.
KCL equation has no meaning. Okay. And here we can say for this figure we have 2 nodes with 3 branches. Okay, so we have one of these and one of these. But we just have one independent KCL equation. You know, understand? You can say this one and this one. The reason is we have to choose one as the reference node. Understand?
Yeah.
One as the reference node. So for another node, we write the KCL equation. Understand? So for KCL equation, the first thing is we have to choose one as the reference node. Okay, so the equation of KCL will be n minus 1. The 1 is for the reference node. Now we are going to say the KVL law. It is the Kirchhoff's voltage law. It is stated that the algebraic sum of all voltages around the closed path is 0. Do you remember the definition of the closed loop or a mesh? Closed loop or mesh. Remember?
Yeah.
Okay. A mesh actually an independent loop. Okay. So here is the algebraic form of KVL law. This is one form, and we also have other extended form. And we have the sum here for Vm, m for 1 to n equal to 0. Here m is the branches number in the closed loop. Vm is the voltage of the mth element. Understand? Okay, let's look at the simple example. This one is the figure we showed before. Okay, we say we cannot have any use for KCL law, so we will use KVL law. So now I just showed you some steps to solve a problem. Okay, so for this case, On the first step, we need to select a reference direction and start from any element. Here I select the clockwise, and you also can select counterclockwise as well. Okay. Here in this example, the direction of the voltage is given. But in most of the case, the direction of voltage is not given. For that case, we need to select the sign by ourselves. So what's the direction of sign we choose? For what? For the active convention or passive convention? Because this one is a passive element.
For passive convention.
Yes, for passive element we use passive convention. For active element we use active convention. Remember? Okay, remember it by heart. But you should notice if the direction is given, you have to follow its direction. Okay, if it's not given, we use the active or passive convention by ourselves. Okay. So here I choose the clockwise. The reason is for this one is the source.
Yes.
Generally the current is go out from the source. Okay, and then for this one go inside from the positive side. Okay, so that means the passive sign convention, right? Okay, because this one is resistance, it is the passive element. Okay, and this one as well. But here we say it's going side into the negative side.
It's active element.
But here we use active convention.
Yes.
So it's also positive, okay? And then go inside here. So from this figure we can say if we choose the clockwise direction, all the values should be positive, okay? So we choose the clockwise. The step 2, add voltages clockwise or counterclockwise. And on the step 3, we decide the sign of voltage. If we met plus terminal first, positive, met minus terminal first, negative.
It's actually more familiar.
Yeah. So here in this example, we start from V2. So V2 going inside into the positive, so should be positive, and going to V3, and then going to V4, okay, minus, and then going to V5 and minus 1. And we can see if we move the V1 and V2 to the right hand side, it will, because the right hand side is the source, the left hand side is the load, right? So it is still obey our active convention.
Yes.
And we can say the sum of voltage drop is equal to the sum of voltage rises. Okay, this one is another form of our KVL law. And for the KCL law, we know the current on inside is equal to the current on outside. And for KVL law, we know the voltage go up is equal to voltage going down. It is because the energy should be balanced. Okay, so it cannot generate and it cannot eliminate it. So you can just transfer from one part, from one item to another item. Okay. So we have up and we must have down. And we have go inside and we must have go outside. Okay, the third extension, the equivalent circuit for voltage sources in series. Please look at this figure. This figure is the original circuit of voltage sources in series. Okay, this one is its equivalent circuit. And we say if those two circuits are equivalent, they must have the same UI relation on the port A, B. Okay. And for port A and B, if we connect R on the R2 circuit like this one, and we can say if the I is the same and VAB is the same, those two circuits are equivalent. Okay. For this port equation, our VCR equation VAB to IR should be satisfied. And for the value, for this side, we draw a loop like this one, and we can write our KVL equation like VAB, here is the VAB, is equal to V1 plus V2 minus V3. Okay?
Yes.
Because the voltage here is equal to the voltage here. Okay? Understand? That means if we choose any two nodes of a loop, this one is extended KVL. If we choose any two nodes of a loop, and on the left part, the voltage on the left part is equal to the voltage on the right.
Right part.
Okay, understand? So for this one, because this one, do you know the potential? Do you know the potential? Potential.
Yeah, potential.
Okay. For one node, the potential is a value. Okay, it cannot be changed if we choose the same reference. Choose the reference potential. Okay, if we choose the reference point, the same. The potential cannot be changed. So VAB is actually the potential difference. Okay, that means for this node A and this node B, the potential difference cannot be changed. So it cannot be changed. We don't need to care about the paths. Okay, from here we can use this path to here, and we also can use this path to here. But the voltage difference is the same. Understand? So that is the reason we say VAB is equal to V from here, here, here. Okay. Then we get our KVL law as VAB to V1, V2, V3, and we can see here the positive sign is up. Okay. And this one, the negative is up. Okay. Therefore, we say if this one and this one is equivalent, we have to make this VS equal to VAB. Then they have the same UI relation on the port. Okay. So here is the interference. The voltage between 2 points is not satisfied to the root. That means we can choose any node from one node to another one. Any node. The voltage or the potential difference should be the same. The voltage is scalar, satisfies this equation. Our E is a vector, and we use do you know this? Integration. Okay, we use this integration and we get our potential difference. Do you know this? The dot. What does this mean?
Dot product.
Yes, dot product. You know how to do this. Dot product A dot B.
AB cos theta. AB cos theta.
AB
Cos.
sine theta.
Yeah.
Okay, remember this one? You know this equation? And
AB sin theta is have the unity vector.
This, how to say this one?
A cross B.
A cross, okay, this one is a cross.
Yeah.
A cross B is equal to
AB
A
sin
is on sine
theta.
AB and direction is 3. The 3 is satisfied the right-hand law from A, B, and this one is the C.
Direction.
Like this. This one is direction A, and this one is direction B. And now this one is direction of C. This one we talk like the right-hand is the right-hand law.
Yes, right-hand rule.
Right-hand rule or
Yes.
right-hand law?
It's
Okay, anyway. Okay. Now we're going to see the equivalent circuits for voltage sources in parallel. Okay. Only for the voltage source with the same V. Okay, it just can with the same V. Do you remember we talk about the current source in series?
Yes.
The value of the current source
It's
is
same.
also should be the same.
Yes.
And for this case, we have
Voltage.
some voltage sources connected
Parallel.
in parallel, and they also should be
voltage
with the
is
same value.
Yes, ma'am.
Okay, and we know the equivalent is for the port. Okay, so we say if this one and this one is equivalent, they must have the same UI relation for the out circuit. So we know the voltage difference is decided by here, but by V. So VAB is also V. And our current is decided by what? Our current by the outer circuit. Okay, why? Because the voltage is decided. Okay, it cannot be changed. It's decided by the voltage source. We cannot change it. So this one is a special case, and here we have a voltage source here, and we connect any element here in parallel, and we say this one is the equivalent circuit for the outer circuit. And the reason is if we connect a resistance on the outer circuit, we notice the VAB is still V, right? Because the voltage is decided by the potential difference of these two nodes. Okay, so the voltage will be the same. And for R, we know VCR, our voltage current relation, Ohm's law. Okay, so the I should be I equal to what?
D by R.
V over R. Okay. So we cannot ignore this one if we want to know the current going inside into this branch, right?
Yes.
If we don't need to consider this one, then we can delete it. If we want to know the current going inside into this one, and we have to leave it alone. But for simplification, if we want to simplify a circuit, we just delete it. Okay. Okay, now we're going to see the basic circuit analysis method, 2D method. This one is the most basic one. And we say, for any circuit, we all can use this one to solve it. But it doesn't mean this one is a very good method. From the name of this method, we know 2B. What does this mean? We know B is the number of the branches, right?
Yes.
This method means we have 2B equations for this method. Is it a large amount of equations? 2B, 2 times 3. Is it a large amount of equations? 2B.
Large amount?
Large amount of equations if we use 2B method. I just say B is the number of equations. For example, if we have a circuit, it has 8 branches. Okay.
Yes.
And the equation number will be 2 times 8.
It's large 16.
So, for this example, you know, this method might not be a good choice because the number of equations is too much. Okay,
Yes.
so what kind of equation we want?
Loop.
Well, yes, one loop, okay, something like a source and a law like this, and we can use Ohm's law, right?
Yes.
That is the simplification. That is the simplest case we know, and this is our purpose, okay? And we might maybe have an inductor or capacitor want this one. Maybe for this one we just have one equation, but for this one we have six equations. So that is also the reason we want to simplify circuits. Okay. Okay, now I just want to introduce this method, and we know this method, but for simple cases we can use it. But maybe for cases with if b is over 2 or over 3. If it's 3, okay, we have 6 equations.
Yes.
So it's not good, right? If b is equal to 4, we have 8. But if b is equal to 2, you just have 4. It's not too much, right? Okay. So for this method, maybe we say if we just have 2 branches, we can use this one. What does 2 branches mean? One branch means
one branch equals 2 equations.
One branch is like this, a branch with some elements, but has the same current, right? But another one, maybe something like this. Remember? Okay. For a circuit with B branches and N nodes and L independent loops, we can find out B branches voltage and B branch current. You know branch current?
Yes.
You know branch current? What does branch current mean? The current on a branch. Okay. For B branches, we can have B element constraint equations. Element constraint equations. Maybe for resistance, we have VCR equation. Our V equal to IR. For inductor, what do we have? For inductor, what do we have?
For inductor, V equal Ix X equal
for L, what do we have?
For L.
For L, for inductor, what do we have?
So V equal L di by dt.
L di over dt.
Yes.
Good. Well, what for capacitor? What is it? The VCR equation.
I equal
C.
B is dV by dt.
Good. So those three VCR equation we have to remember it by heart, okay? And when we will talk about it, you can write down it in 1 second. Okay. So for N node we have N minus 1 independent KCL equation. I just took it. Okay, so we choose one node as the reference node, and we can write down N minus 1 KCL equation, right? And here we have L independent loops, and we have L equal to B, the number of branches, minus N plus 1 minus this one. Okay, B equation minus this equation, and then we get the number of KVL equation. Understand?
Yes.
Okay. Then we remember this relation. The number of B minus the number of independent nodes. In number of branches minus the number of independent nodes. Okay. And here we can say N minus 1 equation. Here the KCL equation number plus the KVL equation number plus the VCR equation number is equal to 2B. Clear? So that is the name of this method, search function. From the number of the equations, we have 2B equations, so this method is called 2B method. For these methods, our variables is not I and V anymore. It is the branch I and branch V. Understand? So we need to suppose a branch I or suppose a branch V before we do this.
If we have one more for this equation N minus 1, if we have one more, so
we don't use any we don't use any KCL equation, we just have KVL equation, clear? Because I just told if there is no independent node, it's all one node inside, connect one element and another one. The current go inside is the current go out. This equation is no use. Okay. Okay, please look at the example of Kirchhoff's law. Okay, I talked about this example and also want you guys to finish it by yourself. Follow me, okay? The circuit parameters are as shown, and we need to determine the V0 and I in the circuit. Where is the V0? This case is a little bit different because we have a dependent source inside. Okay, this one is the voltage controlled voltage source. Clear? Here is the controller, and here the diamond means is a control source, and the sign and minus sign, positive sign and minus sign means this one is the voltage source. Okay. So, okay, 10 minutes break. Oh, okay, I finished this one, and 10 minutes break, okay? Okay. And our I didn't say I here. Let me have a look. Where is the I? Oh, okay. Because this one just has one loop, okay? It has just one loop. Or can say it just has one current, but we don't know the direction. It doesn't matter. We can give the direction maybe like clockwise. So we analyze this one carefully, and we consider the law to be applied. Here we can see we have node number n, independent node number. It's not node. Okay, node number n is equal to 0. Clear? And loop L equal to 1. Because here we just have one mesh. Okay, so we say in most of the case we consider a mesh as the independent loop. Understand? So here our loop number L is equal to 1, and our branch number B is equal to 0. Okay. So for this we can say we just have one KVL equation. Understand? Clear? Okay. So the step 1, we can say our unknown variables is V0 and I. That means our objective is to find out the relation for V0 and I. That is our objective. That's two unknown variable needs two independent equations to solve this one. Understand? We need two algebraic equations for these two unknown variables. That is from mathematics. Understand?
Yes.
Two unknowns, two equations. Three unknowns, three equations. Four unknowns, four equations. Okay, but those equations should be independent. Understand? Then step 2, we select the reference direction of our current, because we didn't define the current before. So our reference direction I, we select the clockwise, and the reason is we just tell here we select the non-associated direction, reference direction, or active convention for this one, for current, for the source. Okay. And on the step 3, we write the KVL for loop I, for the independent loop I. Okay, because from the analysis we say we just can write out a KVL equation, no other equation. Clear? So we write KVL equation for I and the Ohm's law equation for V0. This one is because we need to add one equation for the controlled sources. So if we see any controlled sources in the figure or in the circuit, we must know we have to add one more equation. Understand? Okay, so for KVL equation here, we can say, choose this point and this point, okay? Maybe we can put one over here and one over here. And we know that the voltage difference is 12, okay? So it must equal to here, 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 the voltage sum of the voltage here. So here we choose, it doesn't give me any reference direction for the resistance, okay? So we can choose passive sign convention. So here we can choose the positive here, so it should be positive, okay? So I didn't make any sign here, but remember it by heart. If it is resistance and if it didn't give you any direction, just use passive convention, okay? So here should be I plus I times 4, okay? And here go inside into here.
Positive.
Okay, so it should be positive, should be 2V0, the voltage. And then it's going here should be minus 4, okay? And then going here, minus as well. But we can use I minus 6I or V0 as well. Because here we know our VCR is I times 6. But here we also have the value of V0 here as well. So we can use both of them. Understand?
No. I don't understand.
I mean, here for this part, if you put,
it should be minus. No.
yes, it should be minus.
Yes, okay.
It should be minus. Okay, it should be minus.
No, it's okay.
I know, just a simple mistake.
Yes.
I want to go back on my channel. Never mind. Okay.
You mean this first line is coming like this, minus 12, 4i plus 2 into minus 6, minus 0?
And here I use I just because I suppose positive sign is here. You understand? Because it's supposed the positive sign is here. So that's the reason I use this one. And you can see the minus, I put them here. Understand?
No. How is the minus of 6?
That's because I put the positive here. You know?
But
In my mind, I use passive sign convention. So this one is from the passive sign convention, and then from this one we need to find out the VCR equation for this one. So for this one, our V0 is the positive signs here is negative, is opposite to the 6I. Understand? Okay, so if we have a resistance here, if we have I inside, we have 6 ohm here, so it should be 6I, right?
yes.
So if we say this one is V0, so the V0 should be minus 6I. Understand? Because we change the direction of V.
Yes.
Understand? So the equation is right actually. Understand?
Because if the step like the 6I is directly, our first equation is minus V0. So V0 equal minus 6I, so
The
minus
result should be the same.
Same.
This result should be the same. Just because here I didn't follow the direction of minus V0. I just write down a KVL law, use my direction. Then I find out a relation for V0 and 6I. For this resistance, and I got this one. Okay, 10 minutes break and you can try it by yourself. 10 minutes?
It's finished.
I know, but 10 minutes break. Number 2 should be 3I2 equal to 6I3, right? This should be this one, and this one, the third equation, and then we get our result. For this one, I2 equal to I1 equal to I2 plus I3. So we can say inside here we have variables I1, I2, and I3. 3 unknown variable, 3 equations, and we can get I1 and I2 and I3, right? And then we still need to get V1, V2, V3. So we still need those 3 ohms equations, and we put out our I1 here, I2 here, I3 here inside, and we get V1, V2, V3. Understand? And then we get all the value we want. And we also can use this method. This method is called the loop current method. This method is loop current method. You can see here, for those 2 equations, we will get I1 and I3, okay? And then we use this one, get I2. And then put them inside and use those 3 equations, and we also get the same result. That's the same actually. The same results but different way. You can see here, the I in loop 1, the I in loop 2. And then we can solve the equation and we get the result. And here I use a figure to say the difference here in the V2 in the 3 ohm. You can see here the loop I is this direction, the loop 2 is this direction, and I2 is equal to I loop 1 minus I loop 2. Understand? So that's the difference here. VAB1. What is VAB1 for? Here VAB 30 minus 8B1. Okay. Here we calculate the V1. V1 is here. What does that mean? You already get V1. Okay, VAB. But VAB is equal to 2. We don't need to count the VAB.
So they do it same way, but I have little bit different result.
Up to class, okay. There's 2.5 section series resistors. This one is a simple example. We have a single loop current here, and this one is the equivalent resistor here. If we have 2 resistors in series, and we can calculate the equivalent circuit for those 2. We should have the same UI relation for node A and node B. We can do a simple analysis here. In this equation, we just has one independent loop. Our L equal to 1, so we can write down a KVL equation for the loop current I. And we also can write down 2 ohms equation for V1 and V2 because our inside here our V1, V2, and I are unknown, so we need 3 equations. For KVL law, we have our V equal to I times R1 plus I times R2, and we get this one. Because this one should have the same relationship, so our V should be in this form. Our V should be equal to I times R equivalent. So our R equivalent should be the same, have the same V value as R1 plus R2. Our R cubed should be equal to R1 plus R2 if we have two resistors connect in series. Okay, and we get our I to V over R1 plus R2. For Ohm's law, we get the result of I. Okay, and for Ohm's law, we have V1 equal to IR1 and V2 equal to IR2. And we get all of the results, all of the unknowns. And the problem is solved. And you can notice, for V1, we can put the value of I inside, and we get this one. And we also can put the I inside this equation, and we get this one. Observe those two equations. What do we have? We can see the denominator is the same. And the V is the same. The only difference is the denominator. For V1 is R1. For V2 is R2. What does that mean? Means the value of V is proportional to the value of resistance if they are connected in series. Okay. So it also understands our the voltage divider. We use two different resistors connected in series to make voltage divider. Okay. Here we have series equation equivalent R and voltage division. The equivalent resistance of any number of resistors connected in series is the sum of the individual resistance. For n resistors in series, in last example we have two resistors in series. Okay. Now we have more. We have R1 to Rn resistance in series. And the single equivalent resistors, we have this one. So if we want to use this circuit to stand for this one, what should be the value equal to? For Ohm's law, we have the VCR equation, V equal to IR cubed. And for this one, we can write our KVL equation, right? So our V here is equal to V here, until V here, the sum of them. So we have this one. This one and this one have the same UI relationship. On the left hand side, it's V. On the right hand side, here is R cubed. Here is IR plus until Rn. So we get R equivalent equal to R1 plus until Rn. And we use this one to stand for it. A sum symbol from n equal to 1, sum to n, Rn. Okay. So we need to remember, we don't want a long equation, right? So we use this symbol for this one. Okay? We need to know how to do this. So this one is the voltage divider I talked before. For Vn, the voltage division, our Vn should be equal to the value of this resistance over the sum of all them, sum of the resistance in series times V. Okay, it's proportional. And we put this symbol inside, it should be written as Rn over the sum of Rn for n1 to n product V times V. Okay, now we're going to see the parallel resistors. This one is an example. Okay, this one is the original circuit, and this one is equivalent circuit. And we say if we want to use this one to stand for this one, we need to have the same UI relation. For this one, we can simply get the VCR equation I times R equal to V, right? So our I is equal to I over Req times V. Clear? And the same UI relation is in this form. I should be equal to something times V. And what is the something for? And we can analyze this one. For this one, we have two nodes for one KCL equation. This one is one node, this one is node B. Okay? So choose one node as the reference node and another one we can write a KCL equation. And here we have three unknown things. One is the I, another I1 and another I2. Okay? So for KCL equation for node A, we can have I inside is equal to the I outside. So our I equal to I1 plus I2. And from Ohm's law, from this block and this block, we have our V to I1 plus our I1 times R1 and V equal to I2 R2. And we can get our I1 equal to V over R1 and I2 equal to V over R2, right? If we put this value inside this one, and we get this equation. Clear? And now the next step, we need to make this equation in the form of this one. And we can take the V out of those two elements, right? And we get this one. Now we can see the left hand side I and right hand side V. And for the red part, it should be the same. And inside this equation, the red part is this one. And here we don't know. And here we have this one. So we have this one equal to this one. They are equivalent. Clear? So for this case, our one over R1 plus I plus 1 over R2 is equal to 1 over R equivalent. And we can write the R equal to the product of them over the sum of them. Please remember this equation, because in most of the case we have two resistors connected in parallel. So we need to remember this equation by our heart. Now we're going to see the current division of I1 and I2. From this equation, the Ohm's law, we can have I1 equal to I eq over R1 times I. Clear?
Yes.
And then we put the value of Req inside. Clear? The value of Req inside. Req is here. Clear? And we get this equation. And it can be rewrite like this one. And you can see here, this one, we get this from the singular procedure, we get the I2. We can write the I2 like this one, and we observe those two equations. We can see the denominator is the same, right? The I is the same as well. The only difference is the denominator. And here, the left hand side I1, the left hand side R2. That means it's not proportional. It's counter. It's not counter. It's part.
Product.
No, it's not
Proportional.
导数 protocol.
Proportional. Proportional.
No, I mean it's 1 over something. What is this? What is this? What is this? I can check it myself.
Crestanovatic. Disproportional logic.
No, that's proportional.
Disproportional.
Disproportional.
Yes.
Wait a minute. I don't
Infinity. Sorry.
Reciprocal.
Reciprocal.
Yeah,
But
reciprocal.
1 over 0 is infinity.
It's reciprocal.
Reciprocal.
Reciprocal. It has name. Okay. So that means the current going inside this is inverse ratio or reciprocal. Okay, that's the same as actually.
Is this proportional? Is it?
Yeah. Okay. But it's not. If we say this proportional string, because it has proportion, but it's different because this is R1, but it's not R1. It's R2. Okay. So we cannot just say it's this proportional, but it has a proportional, but not the normal one. Okay. For R2 is R1 over the sum times R. So it's a kind of current division. That means if the resistance is large, the current going inside is less. If the resistance is less, the current going inside is large. Just remember this, okay?
Okay. How about this one? I will equal.
Well,
That is it.
How about this R1? How can you get this R1?
from this one,
Oh,
from this one, put IRQ inside here, put this one inside here, and we get this equation.
so B equal.
V to IRQ.
But
So this one is V. This part is V over R1. Clear? Understand? Okay, now we can see the parallel equivalent R and J. What is J for?
G
R for
conductance.
resistance.
Conductance.
Yes, R, G for conductance. The equivalent resistance REQ of two parallel resistors is equal to the product of them resistance divided by their sum. So for n resistors in parallel, our 1 over REQ is equal to 1 over R1 plus until 1 over Rn. No general equation of current division, because for two we can get the relation like our I1 equal to R2 over the sum plus times I. For 2 we can get it, but for 3 we cannot get this general equation. We have to calculate it by ourselves. Okay, let us have an example. We have two conductors in parallel. So actually conductance is reciprocal of the resistance, but in our figure, in the circuit figure, it is the same. We don't use any different symbol. It has the same element symbol like R, like resistance, which is different G or R to stand for the value, because it's just reciprocal, the relationship. Okay. So please look at this one. We know our equivalent resistance satisfies this relation. If we let our I over R equal to G, the reciprocal would be right, and we can write it in the form of G. Our G is equal to G1 plus G2. Why we introduce the conductance? Would you please tell me? Why do we introduce the conductance? The reason is it is easy to write math equation. We can have a look. You can see for this one, for this expression, we cannot get a general equation for current division. But if we use the G, we can get it. Let's have a look. For this one, see here, R1 and R2, and now I change the notation to conductance, and we have G1 and G2, and G2. Everything is the same, just change the notation, okay? And then now we have the current I inside. We have I equal to V over R, right? But if G equal to 1 over R, so we can use the G times V. Clear?
Yes.
Then we can get the two conductors current division. If we have I1 equal to G1 V, clear? I1 equal to V over R1, clear? And for this equation, we can get this one. V equal to I over G eq. And this one, we can get I1, put this value G inside, and we get this one. Clear? And then we can derive this one, because our G eq here is equal to G1 plus G2. And now we can see this is proportional. Clear? Our I1 is equal to G1 over sum of G times I. Our I2 equal to G2 over sum of G times I. Okay, so our conductance is more convenient in parallel. We can see from the example, the equivalent conductance of resistors connected in pairs is the sum of all individual conductance. Our G is equal to G1 plus N0 Gn. It is like the equation of resistance in series, right? So if they are connected in parallel, most of the cases we use the conductance to notify. Okay. Okay. Now we're going to see the current division. For n conductors in parallel, the current in conductance is proportional to its conductance, like this one. So we can see if we use resistance to notice resistance to state the current division for n resistance in parallel, it is quite hard. But if we change the resistance to conductance, it is easy to get this relation. And we also can find this equation or this expression is the same as the expression of resistance in series, right? Is it the same one? We just change the V to I. Clear? So that means if we use the conductance when resistance is connected in parallel, we have less work to remember equations. Clear? Okay. So remember it in your heart. When resistance is connected in parallel, just use conductance. Okay. If connected in series, just use resistance. It is the same, just the value is reciprocal. Clear? Okay, please look at this figure. Our Req here is equal to R1, R2, R3. The product over R2, R3 times R3, R1 plus R1, R2. This value, maybe we don't need to care about where it comes from, we just calculate it. Because here we have 3 resistance connected in series. I just show you, if we introduce the conductance, the case will become easier, okay? And here we know our Geq. Okay, we know Geq, G1, G2, G3 from P1. And our I1, okay, for node A, we can write this equation. Okay, from this one, the current division, we can write this. So our I2 and I3, we can get this one and this one. Here, I might miss something here, I think. Let me have a look. It's break time. This equation might be wrong. This one might be wrong. But this one is correct. Here I might miss the I here, and it cannot be like this.
losses. That's problem. How this one equal to this one to beware and beware.
This is a little.
What does it mean?
This is the power.
Yeah.
GN,
Yes.
GN, here, the 1 over Rn, yes, value 1 over Rn.
I can get it.
So then, here are 1
And we don't have all of that. We just teacher gives storage to go. In the day, we use a teacher with so many other rooms. Because my teacher to go.
We have 3 in series, we have 3 in parallel.
Missionary কথা ছিল কি তোমরা এটা অবশ্যই করবে না আমি তোমাকে এক্সাম্পল অবশ্যই জমা দিই তোমরা এটা
And we also get I in here from this equation because of the current division it is easy to find one.
আরে টিচার কইছো না দিন আমাদের যে ম্যাটেরিয়াল দিছে আমরা তো জানো না বাবা অবশ্যই জানো কিন্তু আমাদের কইছে যে যারা আমাদের ম্যাটেরিয়াল দিছে পড়াশোনা রেখে the teacher is bang the this is আমরা এটা কম যাওয়ার 2-3 মাত্র ক্লাস হচ্ছে ফাংশন আমরা অবশ্যই কন্টাক্ট করব আমরা যাবো পানি তার সমস্যা পানি না হলে সেই ইসলামকে অবশ্যই 2 দিন ক্লাস হচ্ছে সেই সময় তো টিচার করব যাওয়ার এই জন্য যত সবই দিলাম তো 2 দিন ক্লাস হইছে
I just want to compare this one. It's a wire. Okay, so it can be considered as 1 volt. So the 18 and 9 are in parallel. So our R 18 parallel with 9 is equal to their product over their sum, and we get 6. And then we can redraw this figure like this one, here and here. Clear? And now you can see it's more easy, right? And we see those 2 are in series, and those 2 in parallel. So we can write it like this: 4 plus 1 parallel with 20. It should be like this. Okay, in your homework, you also can write this like this. Here, see the footnote. Is it we call this one as a footnote so postscript. Postscript.
Yes, it's script.
Postscript.
It's downside on left. Right side. Script, yeah.
Understand? Okay. And then we get it's this one plus 5, right? And 20 and times 5 over 20 plus 5. And we get it 4. So, and we redraw it again. It's like this. And then it's clear those 2 in series and those 2 in parallel. And we can get 6, where is 6? Here is 6. 4 and 2 in series. And in parallel with 6, right? And then in series with 16. And we get this one. Our RAB is equal to this. Is equal to 19 ohm. Here we should notice if we have 2, please notice, if we have 2 resistance in parallel and they have the same value, the equivalent should be half of it. Remember? So this equation we should remember by heart. Okay, now we are going to see example 2.11. Please find the equivalent RAB for the circuit. Okay, here are 2 figures, but the same. One is in the format of conductance, and one in the format of resistance. Clear? Reciprocal, clear? Here we can use 2 methods to solve it. The method 1, capital G, and then use R equal to 1 over G. Another method is just calculate R equal directly. Which one is more easier? Which one is more easier? We know for parallel we want to use what? For parallel we want to use conductance, right? So for here it can be like this. It's equal to 20S. Our REQ equal to R1 plus R2. Our GEQ equal to this one. So here we can write, now it's 5 in parallel, in series with 20, and in parallel is 6S, right? So it should be 6 plus their product over their sum, and we get 10 Siemens. And similarly, if we use the resistance, it should be like this. Those two in parallel, complicated, right? And then in series is easier. But here we have 2 parallel and 1 series. So I think this one might be easier because we just have 1 series. But here we have 2 parallel. So for this case, we know which one is better, right? But the value should be the same. Here we get 10 Siemens, and the REQ should be 1 over it, right? The same as this one. And here I show the calculation process. For this process, it should be like this. If you calculate it by hand, it is easier to get a mistake, okay? Okay. Now we're going to see the Y and delta transformation. This one is also an important part for us. The reason is our electricity of our life is alternative, right? We have 3 phases, and for one phase we might have a resistance, or we might have a inductance. So in most of the cases we cannot avoid to use these transformations. So that's the reason we need to study it. Please have a look. This one is the most easy case. For this case, our resistors are neither in parallel nor in series. Please have a look. Here, this connection, we say this one is a Y connection, or T connection, or T connection. T connection is like this. It's a big T, right? And this one is the reciprocal T. Inverse Y. This one is inverse Y, and this one is the T, big T. And here we can see the differences. For this network, it has 3 ports, right? 1 is here, 2 is here. And for the T, we divided this node to 2 ports. So for this one, we have 4 terminals. That's the difference. But for most of the cases, this one can be turned into this one directly, okay? This connection is called delta network or pipe network. If we split this node like this, because here is just a wire, right? So we say a wire connected between 2 nodes can be considered as 1 node. And we also can break it, right? And to break it, this one has 3 ports, okay? And we can change to 4 terminals. Clear? That's the main difference. But actually, I think it's the same. Just the name is different, and we take maybe different terminals, different number of terminals. The main purpose of this is for circuit simplification, because in most of the cases we have resistors in series and in parallel, But we also have some connection, they are not in parallel or series. They might in Y connection or in delta connection. So for these cases, if we change this one to Y connection, they might become parallel or series. So it's simplified. That's the reason we use Y to delta connection or delta to Y connection. Our purpose is still the same, to simplify the circuit. Okay. So, to simplify the circuit, the first step, we need to identify them if they occur as a part of the network. That means to find out, to locate it. The step 2, we apply Y to delta transformation to simplify the circuit, or delta to Y connection. That's the same. Okay, please look at the model of Y and delta networks. Please notice it is maybe hard to remember the relationship. Okay, this one is a 3-terminal network, a delta network. Okay, or some people you can call it triangular network. Okay. Here, we have node A, B, C, and we have resistance RA, RB, and RC. This one is a Y network. This here, look at here. RA is node A, pointing here. Okay, it's opposite to the node A. RB, RC is here and here. Please remember, we cannot change the name direct by ourselves because we have equation. Our equation is just for this notation. If we change this one to RA, change this one to RB, change this one to RC, the equation is not satisfied. Understand? Okay. This one is a simple connection of Y network. And we have a neutral point inside, and it's here A, B, C as well. But here our R1 is here, pointing to RA, R2 pointing to RB, RC pointing to RC, R3 pointing to RC. Remember? Okay, so let's go back again. A is here, RA is here, and R1 is here.
Yeah.
Because okay, the mirror is like this for A, B, C. So it's a triangular. So RA, B, C must be on the line of the triangular, and we have the connection. Okay, so 1, 2, 3 is another kind of connection. It's inside. Remember, the number is inside. Okay, the number is inside. The vocabulary is outside. Is it vocabulary? No, the letter is outside. Number is inside. Number inside. Number outside. Number inside. Letter outside. Okay. Here is a delta to Y conversion. Equivalent Y is here. If we want those one and those one is equivalent, we have two conditions, right? It must have the equivalent UI relation. It has the same current parameters on a pair of terminals. What do we mean a pair of terminals? It means this one, okay, and this one. This one is here and this one is not here. Clear? Okay. So that means our terminal 1, 2 should have the same REQ. Our R1, 2 here means equivalent Y. REQ. Open this part, open ports 3 and 4. We have R equal to R1 plus R3. If we connect a voltage source here. Here we have R12, port 12 of delta connection. It should be this. And we also can connect the voltages here. And it's like this. It's going inside here and here and go back. Clear? And you can see this one is the form or U isolation of port 1. Clear? All V equal to I times R12 of this one and this one. The difference is just the notation in the bracket. This part is delta, this part is Y, and other things is the same. So our purpose is make this one and this one equivalent, right? Because now they have the same form. And the next step, we just need to make them have the same value, right? Okay, make them equivalent, and we get this one. So our R1 plus R3 should be equal to this one. Similarly, for port 1, 3, for port 3, 4, 1, 3 for port 3, 4, we also have the similar result. And rewrite it, we get these three equations. The resistance inside is our Y connection. Our Y connection for R1, R2, R3 is equal to this. It's equal to the product. R1 is equal to the product of their neighbor. You know, you can suppose
DC
is here. So these two
is
are their neighbor. The product of their neighbor over their sum. Clear? Can you look at R2? The product of their neighbor, right? Over the sum. Here, the product, is it R3? Okay, R3. The product of their neighbor over their sum. Is it easy to remember? So, okay, it's easy to remember, and we still have to remember the R1, R2, R3 is inside for Y. And RA, RB is outside on the line of the triangular. Clear? Because node A, B, C. Clear? Okay, now we're going to see the Y to delta conversion. Another, a different one, right? Each resistor in the Y network is a product of the resistor in the two delta adjacent branches, divided by the sum of the three delta resistors. Here is the value of Ry. See here? Actually, this one is a general form of this conversion. Y to delta. A general form. This one, general form. If you cannot remember it, just remember this one. It's the same, okay? R adjacent, product of the R adjacent over the sum of R here equal to Ry. Now we're going to see another Y to delta connection. Just rewrite it and we get the result. The RA, RB, RC, right? Each resistor in the delta network is the sum of all possible products of Y resistors, taken two at a time, divided by the opposite Y resistor. That means for RA, go back to here. For RA,
opposite.
RA is opposite is R1, right?
Yes.
And it's a possible product. This
R1.
one, and this one, and this one.
Yes.
The sum of the possible products over the opposite one. Clear? Product, possible product the same denominator and different denominator. Okay. And this one is the general form for the Y to delta connection. And this one is also important, and we should remember it. I know it's hard, and for me, it's not. It's actually, if I want to use it, I still need to open my book and to make sure, to make sure the figure is the one in my mind, because it's not really clear. Okay, please remember for our Y is 1, 2, 3. For our delta is A, B, C. Do you have any easy way to remember this? Or a song, you can make a song to remember this. Can you? Why? Why you know 1, 2, 3? Like this?
1, 2, 3.
Actually, I didn't find it easy to remember this.
ABC delta.
ABC delta? ABC delta is it clear? No.
No.
I say why you know 1, 2, 3 is clear. Because why you know 1, 2, 3, so delta is ABC. Clear? Is it easy? Okay. Here I say if we have if we have the same y, it will become like this. So this one we need to remember. Why? Because I'm not sure what do you learn from the electron machine. Because in our electron machine, all the connection we use the same resistance. So this one is a general relation. So for us, for other courses, we need to remember this one.
Yes.
Okay. So the R delta is 3 times of our Y. The form, I think you can remember it by heart. The form or the form should be big, because we need a strong house to protect us. Is it easy? Because we need a strong house to protect the sinking side. So the R delta is bigger than R1.
Yes.
Is it clear? Easy to remember? Easy? Easy? So for me, I don't want to remember equations. It's boring. Because if we want to use them, we can check it from the book or from the internet. But it's also good for us to find some easy way to remember it. If we find an easy way, we don't need to open the book. Clear? So we need, the triangular like a house, right? So we need a strong house to protect us. We are inside. We are keys. We say 1, 2, 3, and we need a strong house, and we are inside because we have three keys inside. So the R delta is equal to 3 keys. Okay, remember? Okay.
It's nice example.
Is it a nice way?
Nice way.
Okay. So here I just rewrite it. Y equals maybe 3 over. But I think this one is more easier because we have the sign and we have the story, then we remember it. Okay. Okay, now we show the mathematical relationship. Here, clear the inverse product, right? Now we're going to do an example. Please obtain the equivalent resistance and use it to find our current R. I will use out. Should be delta 1 over delta, and similarly get the result. And this one is Kramer rule. If we are in a mathematical examination, calculator is not allowed, you know?
It's no problem for me, no need calculation.
Yes. In the mathematical examination, calculator is not allowed. So everything we should calculate by our hand. So it's like this way. This procedure we should know how to do it, right? But in our examination, calculator is allowed because we're not mathematical course, right? We just want you guys to know how to do it. If you have better method, if you have convenient method, it's good.
In worldwide math Olympiad mathematics competition last year. When I was in this country, I participated 2 times, and they are like this kind of difficult math, but no calculator.
Yeah, no
This
calculator.
math Olympiad. One time I get 3rd position, and one time I get
In
2nd.
our examination, calculator is allowed, but some function is limited.
Yes.
This one is limited, you know?
Yes, limited.
This one is limited. You just can use maybe calculate the symbol, maybe like you can calculate maybe square or something like that. You can take the square root, just like that. And for matrix function, no, they don't have this function.
Yes.
And for ODE function, they don't have this function. ODE function has solved, you know, or ordinary differential function. We don't allow we use the calculator to solve it. Okay. Okay, now we're going to see the matrix inversion. AX equal to B. That is the form we get just now, right? So for algebraic equation, we can write it into a matrix form as AX equal to B. For this equation, our A is a coefficient. Matrix actually, and we can multiply A inverse for both sides, and then the left hand side we have A inverse times A times X. And this one, from mathematics we know A inverse times A is the identity matrix.
Yes.
So the left hand side is X actually, and the right hand side we have A inverse on the left. So we get another expression, X equal to A inverse times B. And A inverse, what is it? A inverse is equal to the adjacent A over the determinant. Determinant A. Adjacent A. Okay. So here we should notice our A is an n times n square matrix. Okay, the dimension is n. Okay, and X and B are both n times 1 vectors. Why I mention this? That is because for this expression, our dimension should satisfy the calculation rule. Otherwise, we can't get the result. Understand? Okay. Here is the example. Please obtain the solution of this set of equations. Here is the 3 equation rule. Here is the equation array with 3 equations. Okay. For this one, we can easily get the matrix form, right? We can get 3 minus 1 minus 2. Just take the coefficients, right? 3 minus 1 minus 2. Coefficients minus 1 plus 6 minus 3. Coefficients minus 2 minus 3 plus 6, right? And take the unknown variable x1, x2, x3 in this vector, and then put this one on the right hand side.
Yes.
And the given set of equation is cast in matrix form as this one, and then for matrix A, we can get the determinant of it. It's equal to 39. You just calculate it directly, okay? And the adjacent A is equal to this one. What is the adjacent? Adjacent means for this one, here is 3. Adjacent means this part.
Yes.
Here is minus 1. Over the
3 minus 2 minus 2 6.
Move this line,
Yes.
move this column and move this row, and this one is the adjacent. But we should notice here we have the minus 1. It's minus 1
because this I
plus j. Remember?
1 plus 2 is minus
Okay, so here positive. Here positive. Here negative. Okay? And after that, we calculate the result. It should be this one. Because this one, we also should take the determinant of this part, okay? And we get the result. It is of one value. So the dimension of it is 3 times 3 here in this matrix. And then put the determinant of A is 39 inside, and we get the result. And our x here, we know, is equal to A inverse B. Okay, so A inverse we already get here, and we use this one to times the B, and we get the result. Okay, this is the general way we use to get our x in calculation, in our work, in our homework, or in our other courses. This is the general way to get it. When you do some derivation, we also have to use this. Okay. Here, the element of a adjacent A matrix, the same result. Okay. Okay. Now here is 2 practice. Just try it.
Okay.
Try it. Okay. Our A, we need to use minus A times B. Our x is unknown, right? Our A is known. So we can calculate our A inverse. Our B is known as well. So if we get our A inverse and we get our B and we can get our x. So now our job is to find out our A and then find out our A inverse and then find out our B and just make this calculation. Clear? Just try it. 5 minutes. It's easy, right?
Yeah.
So we know the matrix A is the coefficient, and the right hand side, okay, the right hand side, it's constant, right? We move all the constants to the right hand side, and we get our B. And our A is just the coefficient of x1, x2, x3, and then we easily get our A. And try to use command line solve A and B in MATLAB. Do you know MATLAB?
Yes.
And do you study it?
I use this MATLAB.
Yes, but try to use this command. Line solve A.
Line solve.
Okay.
I use line space logic.
Okay. Okay, and then you can get the result. The result is here, and did you get the result? Is it same as this one? Is it same as this one? The same result? Did you get the answer?
No, I'm good.
No, don't use calculator. Don't use calculator. Use your hand. Okay. If you can't do this calculation without calculator, that means when we are out of the electricity, we can do nothing. You know, you understand? If we are out of the electricity, we can do nothing.
Yes.
So the thing, actually, we have to know how to do it.
Okay.
The calculator just help us to save time. Okay.
Okay, no problem. I can do it with my hand.
Okay, try to calculate the A inverse. The A is easy, but A inverse, we still need some time, okay?
One time do it, one will do it. No.
I can do it 2 minutes, how many seconds is it?
1 minus 1 minus 8.
we're going to talk about the fundamentals of electric circuit, the chapter 3. In chapter 3, we're talking about the method of analysis, the circuit analysis method. This part is also the most important part of our course. Our learning objective of this chapter is, in this chapter, we focus on two circuit analysis methods. The first one is nodal analysis. In this method, we use the Kirchhoff's current law. This one is called node voltage method. This one is suited for circuit with fewer nodes. If we have fewer nodes, we use the nodal analysis. And for mesh analysis, this one is based on the Kirchhoff's voltage law, KVL. This one is also called mesh current method, and it is suited for a circuit with fewer meshes. We know meshes means independent loops, right? If we have less mesh, the number of mesh is less than the number of nodes. We prefer to the mesh analysis. If the number of mesh is more than the node, we prefer to the nodal analysis. Okay? Now we're going to see the first one, the branch current analysis. What does this mean? The name of the analysis means branch current is selected as the variable of our equation. So, in this method, our branch current is our variable, unknown variable. Okay, we have learned the 2B method, right? 2B method, we have two element constraints and n minus 1 KCL equation and b minus n plus 1 KVL equation, and some of them we have 2B equations. That is the 2B equations. For branch current method, we have a circuit which has n nodes and b branches. We can write b equations in terms of b branch current. That means for this method, we just have b equations. Please look at this example. b is less than 2b, right? That means if we use this method, the equation is simplified, right? Let's look at this example. It is clearly we have three branches. This one is one branch, branch 2, and branch 3, right? We have two nodes, node 1 and node 2. And our L is equal to 3. Actually, our independent loops are 2, okay? So, now our variable is chosen as the branch current I1, I2, and I3. I already told you guys, for this method, the variable in our equations is branch current, okay? I1, I2, and I3. So, now we write the KCL equation, okay? We use the branch current to write the KCL equation for node 1 here. And KCL equation for node 2 will be this one. And we can see those two equations are dependent.
Yes.
Okay, so we just have one independent equation. So we can choose any one of it, okay? Then we write out the KVL equations for loop 1. For loop 1, we can see our I1 R1 minus I2 R2 is equal to minus V2 plus V1. Clear? KVL for loop 2. And we have I2 R2, here I2 R2 plus I3 R3 equal to V2. Clear? KVL for loop 3. And we have I1 R1 here
Yes.
plus I3
R3
R3 equal to this one, V1, right?
minus.
And here we can notice I put all of the sources on the right hand side.
Yes.
Clear? This one is sources. So we have B minus N plus 1 independent KVL equation. Clear? So actually I think we can just have 2 is enough. Okay.
Because we have two variables, I1 and I2, so two equations is enough.
Yes, I know 2 equation, but here we use 2 is enough. But that is for loop current. That's for loop current. But here we have branch current. We use the branch current as the variable, so we have 3. That is the reason. So this one is not the most simple one. Okay. So here we can notice we have n minus 1. That's 1. Okay, 1 KVL equation and 3 KVL equation, and we have how many equations do we have? We have 3 equations. We have 4 equations. 3 equations actually. Here we should just have 2. We don't need to have this one. The KVL for loop 3. We don't need to have this one. Okay. We don't need to have this one, I think. Right? We don't need to have this one. But
because let's say I1 I2 I3 equal I1 plus I2.
So yeah. No, we should have 3. Because now we are using the branch current method. This one is the 2B method. But for here we just use the branch current to write out KVL equation. So we should have 3 because we have 3 unknown variable here. So this part is for this method, and for the second method we should have this part. Clear? Okay, now we're going to see nodal voltage method. When we use mesh current method for a circuit with N nodes and B branches and L independent nodes, the node voltage method might be easier for a current with node number is less than the independent loop number or mesh number, okay? Less than the branch number, okay? So if we have fewer nodes, we use this method. What is the unknown circuit variable? Our unknown circuit variable is node voltage. So the previous case is branch current method, right? So this method is nodal voltage method. So in this method, we use node voltage as variable. In the last cases, we use I1, I2, I3. Here we might use V1, V2, V3 as variable, and this V1 is the node voltage. What is the node voltage? Okay, never mind. Okay, now we're going to see polarity. The reference node is always the negative terminal for any node voltage. Means if we use the nodal voltage method, we need to select a reference node first. Okay, and then all of the node voltage is the positive terminal. Okay? Why we use it? Because the KVL is always satisfied from node voltages. We have only n minus 1 KCL equation for this method. Okay, let's have a look. We select the node O as the reference node, and then for node 1 and node 2, we can suppose 2 node voltage, V1 and V2. And V1 plus V1 minus V2 plus V2. It's always satisfied the KVL law. Clear? That means if we use the node voltage, the KVL law is always satisfied. So we just can ignore this equation. Just concentrate on the KCL, right? Okay, now we're going to see the nodal analysis with current source. For a circuit with n nodes without voltage sources, now we don't have voltage sources here, we just have current sources. Okay. The nodal analysis is accomplished by 3 steps. Just remember the steps. If we see a case with current source inside, and we just follow the steps. The first step, we should select a node as a reference node. Clear? And we assign voltages V1 to Vn minus 1. Because we have n node, but 1 is selected as what? As the reference node. Yes. So we just have n minus 1 node voltage, right? Okay. Then this one is 3 ground symbols. This one is we commonly use the grounded symbol for this reference node. Because we commonly use the default reference as 0. Clear? The step 2, we apply the KCL law to each of the n minus 1 non-reference node. That is, for V1 we write a KCL law, and for V2 we write a KCL law as well. And the third, we express the branch current in terms of the node voltages. N minus 1 KCL equation with node voltages as unknown variables. We know for V1, for node 1, our current inside is equal to the current outside, right? So our I1 is equal to I2 plus big I2. Big I1 equal to big I2 plus small I1 plus small I2, right? And this one is known. I1 and I2 are unknown, right? And we should write I1 and I2 in the form of V1 and V2. Clear? How to write it?
I1.
How to write I1 in terms of V1?
V1 over R1.
Because we have here, we can see here is the resistance.
Yes.
Right? And we can use Ohm's law to get the relation. We can see the V1 is equal to I1 times R1. So our I1 should be V1 over R1. And here, look at this one.
V1 minus
what is our I2?
V1 minus V2 over R2.
Yeah, it's the voltage on R2.
Yes.
The voltage on R2 is the voltage difference between node 2 and node 1.
Yes.
It should be V1 minus V2, right? That is the voltage difference. And then the voltage difference is equal to I2 times R2. So our I2 equals to V1 minus V2 over R2. Clear? And similarly, we can get this one. And the third step, we solve the equation and obtain the unknown node voltages. So now the unknown variables are node voltages. Okay, clear? And we solve the voltages V1 and V2, and then go back to get our I1, I2, and I3. Clear? Okay, now we are going to follow the steps. Apply to KCL to node 1 and 2. Here we have 3 nodes. We should have 3 minus 1 equal to 2 KCL equation. At node 1, you can see big I equal to big I2 plus I1 plus I2. I use the blue color to stand for the branch. Is it branch current? It's branch current. Okay.
Yeah. And
this one is the source, and this one is the branch current. But this method is not branch current analysis. It's not voltage analysis, right? So we should write the branch current into the nodal voltage.
Source 10 plus 1.
Then use Ohm's law to express branch current I1, I2, I3 in terms of the node voltage V1 and V2. The direction of I conforms passive sign convention. V high minus V low should be equal to IR. So, in terms of the resistance, we get this relation. From this, we get this one. From this, we get this one, right? And from this one, we get this one. Clear? And if we write this one in terms of conductance, it's easier, right? Because it's the same actually, but it looks easier because G1 is
come to product, not divided.
Yes, it's product not divided.
So this looks like it.
It looks like this, but actually the same, okay?
Yeah.
Okay, now if we are going to calculate our I1 to I3, we need to put the V1, V2 back to the equation, right? Back to the node equations. And we get node equations like this one. And we calculate this one. We substitute this equation into the KCL equation. It's not node equation. Into the KCL equation, and then we get the node analysis equation like this one. And we see all the variable is node voltage, not current, not branch current anymore, right? And then we also can use the conductance for this calculation, and we get this relation as well. And for this equation, come on, and we have talked about the mathematics before, and we say this equation are algebraic equation, and we can write it in the forms of matrix, right? And here, if we suppose the variable is V1 and V2, clear? And we move all of the constants to the right hand side. So this part should be I1 minus I2. Clear? And this part should be I2. So we get our B. For our matrix A, here we take all the coefficients of V1, like here. Take all the coefficients of V2, so it should be minus 1 over 2 here. And similarly, for this one, we take the coefficients as well, and we get this A matrix. For this matrix, we already get the A matrix, X matrix, and the B matrix. And it is easy to get results from the computer, from the method, right? And also from the calculator. Here, we also can write this one into the matrix form with the conductance as well. Which one is better? Which one is better?
For me, that is better.
Conductance is better, right? Because there's no derivation here. Okay, no derivative here, just plus. Okay. It's strange. The GII on the diagonal is the conductance of resistance connected directly to the node I, called self-conductance of node I. Do you know? The red part is called conductance. And the back diagonal is the negative conductance of resistance connected between node I and J. Remember, this part is negative, so I use the blue color. So this one is called neutral conductance of node I and node G. Please remember this definition of self-conductance and neutral conductance. And we also, from the electrical and magnetic field courses, we can prove the Gij equal to JGI. This one we had proved in that course. So here we just use the result. What is this one? Okay. So for here, our G12 is equal to G21 equal to minus G2. For node 1, our G11, where is G11? Here, okay. This is our node 1. Our G11 is equal to all of the resistance or conductance connected to it is equal to G1 plus G2. And for the 2, it's equal to G2 plus G3. Okay? And our Gi2 means this is 1, this is 2. G12 is the conductance between those two nodes. It's R2. Clear?
Yes, sir.
Between those two is R2. And we need to add a minus here. So it's minus G2. Clear? So when you see this figure, if I give you any figure, you need to write out the G11, write out the self-conductance and the neutral conductance directly. We don't need to calculate it. We can write it out directly from the figure, okay?
Just give a minus.
The ISI on the right hand side is the current flowing into the node I. What is this for? I'm trying to conclude a general form. Okay, if we know the general form, we can write out the equation directly without analysis. Clear? Okay. So for the node 1, we see I1 is going inside, so it's positive.
Yes.
I2 is go outside,
Negative.
so it's negative. For node 2, just I2 go inside, so just I2, no I1, right? Okay. Step 3, solve the set of equations. And we get the result. Now we're going to see the example. Please calculate the node voltage. Please trying to write out. Okay, now for this step. Okay. Step 1, select reference node. Our reference node is here. Okay? And here we still have 2 independent nodes, right? And we suppose the voltage of the node is V1 and V2. And we label the branch current I1 to I5 arbitrarily. I1, I2, I3, I4, I5. And then the branch current with current source is the current delivered by the current source. Our I1 is 5 because on this branch we just have the current source inside. So we know the current value is equal to the current source value. For this one is the same. We already get the value of I4 because the current source is 10 ampere, right? And then step 2, we establish the KCL equation for those two nodes. It is clearly for this part we have 3 mesh, right? So if we use other method, we might have at least 3 equations. But we just have 2 independent nodes.
So it's easy to know.
If we use nodal voltage analysis, we just have 2 equations. So this method must be easier. Okay, now at step 2, we need to use V1 and V2 to state the current I2, I3, I4 because we already get I1 and I4 here. Okay, so now we just have 3 unknown variables. For node 1, where is the equation? It disappeared. Well, it's disappeared. Where is it? Okay, for node 1, we can write equations I1 equal to I2 plus I3 because of KCL, right? And then we need to use I1 is equal to 5, right? And I2, we don't know I2, right? But I2 should be equal to V1 minus V2 over 4. Clear? And for this one, we don't know I3, but we know this one is V1, right? So I3 should be V1 over 2. Clear? So for node 2, we know KCL, the current go inside, I2 and plus I4, is equal to the current go outside, I1 plus I5, right? And then we use the node voltage instead of the branch current, okay? And here, I2 equal to this one. Where is I2? I2 is equal to here. V1 minus V2 over 4, right? And our I4 is equal to 10, we already know. And I1 equal to 5 here, okay? And I5, is it I5? Yes, I5 is equal to V2 minus V reference. V reference we know is 0 over the resistance 6. Okay. And the next step, we rewrite this equation area like this one because this one is more clear to get into the matrix form, right? And step 3, we solve equations. Method 1, we can solve linear equations, right? And method 2, we use Kirchhoff rule. Clear? Remember? We get this one and then turn it into the matrix form, right? We get A matrix, B matrix, and A matrix, X matrix, and B matrix, right? And then we can calculate A inverse. Look at it, determinant of A, right? And calculate adjacent A, and calculate our A inverse. And then our V is equal to A inverse times B. Okay, this part you also can use your calculator to get it, right? So for this one, we think it's more easier, right? Okay, after this, we get our V1 and V2. Clear? V1 equal to 13.333 and V2 equal to 20 volts. And we substitute V1 and V2 back to the branch current equation. Where is the branch current equation? This one, right? This one is the branch current equation. And we get the I2, I3, and I5. And this problem is solved. Clear? And now we are going to see the example 3.1. Calculate the node voltages. Okay. So first step, what should we do? Select the reference node, right? Then select V1 and V2 because here we have two independent node, right? V1 and V2. And here we use the direct method. For node 1, we can get the self-conductance. Do you remember? We say it equals to the conductance connected directly to the node 1. So it should be 1 over 5 plus 1 over 4. Then, for node 2, we calculate the self-conductance. The self-conductance, like this one, should be 1 over 5 plus 1 over 5. Clear? And then we are going to calculate the neutral one. For neutral one, V1 and V2, we see just one conductance connected between them, right? So it's 1 over 5. Okay, we know the neutral conductance is negative, right? So it's minus 1 over 5. Is it easy? So we can write down the G matrix directly from the figure. And then we know our X is the unknown variable V1 and V2, right? And our right hand side is the I. The current going inside is positive. The current outside is negative. But the right hand side is the source. Please remember, it's the source. So for node 1, here is the current source for 14, right? The 14 is go inside, so it should be shown. And for node 2, and here is 7, and here current source go outside. So it should be what? Negative what? Negative minus 7, right? Because the value is 7, okay. Okay, I don't know what happened here. Gosh. Okay, then we get our A matrix, right? Just from here, and we get the result. And we can calculate the determinant of A directly and calculate adjacent of A directly as well. And our A inverse can be calculated as well. And then we use the parameter rules x equal to A inverse times B. A inverse is this part, B is this part, right? And then we get the result directly. Which method is easier? This one, right? We don't need to analysis it. We just select the reference node and just select or just line the V1 and V2, and then directly write down the self-conductance and the neutral conductance and the B. And then it becomes a mathematical problem. And we use the mathematical skills to solve it. Okay, so for this method, we say it's a short way, it's a shortcut to solve this question. Okay. Now we're going to see the case including current control sources. This one is a little bit complicated. Okay. So here we can see what is it? It's a current control. Current source, right?
Yes.
And step 1, we take this one as an independent current source to write KCL equations.
Is this current controlled current? Yes.
Current controlled current source. And then we express controlling current. The controlling current is Ix. Controlling current Ix in terms of node voltages. Clear?
Yes.
For example, like this way. Our Ix, suppose our Ix is here. And we know our Ix times R is equal to V1 minus V2. So we add one more question like this. So the second case, if we have a unaccompanied current controlled voltage, CCVS, a different case. The first step, we treat it as an independent source with unknown current. We don't know the current, I. And we also write the KCL equations. Then, the second step, we need to find out the controller Ix, right? Go back to this part. We know the Ix times R is equal to V1 minus V2. And the third step, please notice here, for this part and this part, we have one more step. We need to add one more constraint equation of voltage and node voltages. It's V3 minus V4 equal to minus Ix. Ix is here. Minus Ix is here. Okay, so we suppose an unknown current I here. This one is unknown. We just suppose we have I here. Clear? Suppose we have I here. Okay, now we're going to see some examples and to familiar with this one. What is this? It's a current control, current source, right? It is our case 1, is it? Is it? Okay, so follow the steps. First one, select reference node, this one, right? And the label node voltages V1 and V2 and V3. Clear? And then we label the branch current I1 to I3 because we have 3 branches here. Actually we have 4, but okay. So step 2, we write KCL equation for node 1, node 3. For node 1, we have 3. The current going inside is equal to the current go outside, is equal to Ix plus Ix. I1 plus Ix. Clear? Look at node 2. KCL law. The inside is equal to the outside. So our Ix is equal to I2 plus I3. Clear? And for node 3, our inside is I2 plus I1. Our outside is 2Ix. Clear? Because on this branch, here we have a control source, right? But here we know the control source, the value of the control source is 2 times Ix. So we'll just directly write it inside. Clear? Then our unknown variables is Ix, I1 to I3. We have 4. Okay? And we can write it in terms of V1 to V3. Okay, go back to our I1. Then we need to look at this resistor, right? It's equal to the V1 minus V3 over the conductance 4. Clear? And then look at this one. And this one we have V2 minus V3 over 8. Clear? And then we're going to this one. We have V2 minus 0 over 4. Okay, then the third step, we need to calculate the controlling current Ix. The controlling Ix, where is it? We found it is here. Okay, so it is easy to find. The Ix times 2 is equal to the voltage difference between node 1 and node 2, right? So it's V1 minus V2 over 2. So now we get 4 equations. And we substitute this one to these equations, and we get 4 unknowns. And we get this one. Clear? We get these equations. And then we solve this linear equation set, and we get the result. Please think about if we change the control current source to a voltage source. What happens? What will happen? Just think about it. Okay. For node 3, we have where's node 3? We have I1 plus I2 equal to I. If this one is the voltage source. If this one is the voltage source, we just suppose what? Suppose the current goes through it, right?
Yes.
And then for branch 3, 0, and we get this one, 2Ix equal to V3, because this one becomes a voltage source. Now you can see here is voltage source, right? Clear? So our V3 is equal to 2Ix. Clear? And then we get this equation, and we get this equation. For these two, for two node 1 and node 2, we have this KCL equation, and then put the value inside, we get these two KCL equation, and then put it back to get our Ix, and we get the value. Clear?
Clear.
And when you go back home, you can try it, okay? One more practice. Okay, please calculate the node voltages. Is it the same as the last one?
1, 2, 3 nodes.
Is it still a current source, right? So what is this
Current
one?
control current source.
The same, so we don't need to talk about this one. Okay, but for this one, I use the simple method. The step 1 and step 2 is the same, but the step 1 label reference and V1, V2, V3, and with I1, I2, I3. But here we can see we use easy method, shortcut, right? G11 equal to what? G11 equal to 1 over 2 and then 1 over 3. And G22, look at here, is equal to 1 over 3 and then 1 over 4, right? And the G33 is equal to 1 over 2 plus 1 over 6, right? And then we're going to the mutual conductance. Here, 1, 2 should be minus 1 over 3, right? So, G12 and G21 the same. Clear? And for 2 and 3, where is it? No, there is no conductance, right? And for 3 and 1, we can see here, right? The mutual conductance is 1 over 2, minus 1 over 2, right? So the G13 and the G31 is minus 1 over 2. And our variable still V1, V2, V3. And here, the current going side is 4. The current going side into 2 is 4Ix, right? And the current going side of 3, actually it's go opposite, so it's 4 minus 4Ix. And then, write out the controller constraint in terms of node voltages. Ix. Here, our Ix is equal to V2 over 4. Where is it? Our Ix. Here, we can see the relation here is given by this part. We know our Ix times 4 is equal to V2 minus reference, right? So we can get the expression of Ix. And now our Ix is in terms of V2, in terms of voltage, node voltage as well. Then we can change the equation like this one. And we can see all of the variable is changed to V, right? And we can calculate the result. We can remove this part into the left-hand side, right? And we get this one. And this one is easy to get the result. Just use the V equal to G inverse times I. Is it easy? No? Okay, this one is another kind. Okay, we will start this one from the next course, so see you next week. So are you confused or clear? Yes, you need more practice, and I hope you understand. Just follow the steps. I already conclude the steps. Okay, so when you get a question and if you think, oh, I'm not really sure about the steps, okay, go back to my PPT and find the case and follow the steps and find out the results. Okay.